is Tian Zhijian, the research fellow at Dalian Institute of Chemical Physics of Chinese Academy of Sciences, and he is going to talk about the potential of SAF, Sustainable Aviation Fuel market. Distinguished academician Mr. Chen, distinguished guests, I am Tian Zhijian from the Dalian Chemical and Physical Research Institute of China Academy of Science. I would like to thank Anglo American for inviting me to speak at this forum. In this presentation, I'm going to talk about the process and technological development of SAF. So my presentation will have two parts.
First, I'm going to talk about how we have investigated market outlook of SAF, or sustainable aviation fuel. This is not a free market. Instead, policy, government, and economy all play a role here to achieve an equilibrium in the market. So firstly, what is SAF? Or the SAF, its full name is Sustainable Aviation Fuel. It means that it represents sort of aviation fuel that's used in the existing aircraft's engine, but it's sourced from renewable resources or waste, as well as petrochemical. It can be blended with petrochemical jet fuel. Currently, we have two different concepts like HEFA as well as HVO. So the two concepts have overlappings with SAF. As for the jet fuel distillate from HVO, actually it belongs to SAF, the jet fuel distillate. While considering the transportation and utilization, there are carbon emissions. However, the production of SAF is carbon neutral. So throughout its life cycle, SAF represents 80% reduction of carbon emissions. Currently, in the international market, 330 million tons of SAF is consumed, and we'll expect that the number will reach 530 million by 2030 or 2050. So the market is rather huge, meaning opportunities for SAF. Well, why do we need to use SAF to replace existing petrochemical jet fuel? It's to some extent related to China's carbon neutrality and the carbon peak goals. As you have already heard that in 2020, China's President Xi Jinping made a solemn promise that China will achieve carbon peak by 2030 and carbon neutrality by 2060. This corresponds to the various carbon peak and carbon neutrality goals already proposed by other countries. Following President Xi's commitment, China released a number of official documents giving a very good blueprint for carbon neutrality and carbon peak roadmap. According to the European Union, by 2030, they need to increase SAF proportion to 6.8%, and the number will reach 63% by 2050. In America, the goal is to consume 3 billion gallons of SAF by 2030, and by 2050, they want to achieve 100% SAF utilization, which means that by that time, every year, 35 billion gallons of SAF will be consumed in the part or on the part of the United States. For the end users, namely the aircraft companies, they have two considerations. On one hand, they consider cost. It means that they consider whether SAF is competitive with the existing jet fuel on the cost front. That can be addressed by national government's fiscal subsidies as well as a fair surcharge. On the other hand, the aircraft companies consider the security of SAF, and they have a more demanding requirement for safety when it comes to using SAF in airplanes. So from 2018 to 2020, from 2008 to 2018, around the globe, around 30 aircraft companies use SAF to fly 150,000 flights. As of 2022, more than 45 aviation companies have flown 430,000 flights using SAF. Given the 3-year pandemic period, the number of 45 and the number of 430,000, which represents a significant increase from the previous number of 30 and 150,000, represent huge investment on the part of aviation companies on SAF. Some of the major testing done by internationally renowned companies regarding SAF. Currently, The most commonly raised concern about SAF is about its components. Its composition is very much similar to the existing traditional jet fuel, so it's very much compatible. However, it does have some impact on the fuel system seals as well as some components. However, Honeywell has conducted all sorts of testing and experiment on the safety of SAF, and 100% of the testing and experiment items have reported success. Around the globe, aircrafts or airports are very active in supplying SAF to the flights that either stop over or land there or take off from these airports. According to current projection or according to what we can expect from policy stimulus, Europe is very active in supporting policies. According to European Union, by 2050, SAF's addition proportion must reach or exceed 63%, corresponding to a potential demand of 43 million tons per year for SAF. And if the various EU member countries gradually release supporting policies for SAF, we'd expect rapid uptake of the processing capacity of SAF. This chart gives you an overview of the policy support on the part of America, China, and European Union, and how much demand for SAF that means given all the policy stimulus. Europe is most active in releasing policies. However, America is the most ambitious in terms of how much they expect demand will be for SAF. They expect that by 2050, the need will be around 100 million tons, which is almost double the figure proposed by the European Union, standing at 43 million tons per year by 2050. And for China, we haven't yet given any concrete numbers. So we'd expect that by 2050, the number will be 2 million tons per year. So currently, in the United States and in the European Union, the status quo is 220,000 tons per year in America and 34,000 tons per year in European Union. According to IATA's plan or the targets, they expect that by 2050, globally need for SAF will reach 6.3 million. By 2050, the number will reach more than 300 million tons, which means 7,000 times higher than the current 50,000 tons. And a key milestone will happen in 2030. After 2030, despite the absolute increase volume, the 2050 need or consumption is only about 20 times the consumption forecast that IATA has given for 2030. But mostly demand comes from European Union, and mostly production capacity comes from European Union as well. Currently, the EU has existing capacity of 2.4 million tons per year, and an extension is possible ranging or at 1.6 million tons per year. Currently, 13 sets of production facilities with total capacity of 4.5 million tons per year are under construction in the EU, and HEFA dominates the technology pathway in the European Union. So as you can see the figures on the slide, the gap is huge. In terms of America, all the projects are under construction. In other words, the United States doesn't have existing SAF facilities yet, but they have 5 million tons of capacity under construction, with the lion's share being dominated by the G plus FT by ATJ pathway. But still, the 5 million tons represents a huge gap compared with how much America expect their demand will become going forward. In terms of China, SAF is still at very early stage, and we only have biofuel capacity in China. However, there are overlappings between SAF and biofuel. For biofuel, the dense point or the jet fuels solidifying point is minus 50 degrees Celsius, whereas biofuels solidified point is minus 30 degrees Celsius. So we need to do technological upgrade in order to convert it into SAF. But currently, technology conversion projects are on the way. SAF, on the other hand, to a large extent is influenced by the cost of raw materials. As I mentioned, that 80% of the raw materials are biological fats or biological lipids, which are to a large extent influenced by the international energy and crop market. After COVID, the market or the price has gone down to 2017 level at around 8,000 RMB per ton. Whereas for SAF, the current price is 18,000 RMB. In other words, there is still a price difference of 10,000 RMB, and the price difference of 10,000 RMB represents the major driver for developing SAF. So in a word, the SAF market has several things to consider. Firstly, internationally speaking, of the carbon peak and carbon neutrality goals, there are mandatory national policies already released or are in the process of being formulated. And another thing is the price difference between the cost and the price, meaning there are monetary stimulus for the growth and development of SAF. And in China, at the national level, ministries and departments have released the government documents to develop SAF technology. Next up, I'm going to talk about our efforts in researching and studying SAF. So firstly, we need to understand the components of SAF. For petrochemical jet fuel, mainly they're composed of N-paraffins, isoparaffins, aromatics, naphthenes, and alkanes. For SAF production, in the early stage, we rely upon animal fats. Mainly, we rely upon the two components of N-paraffins and isoparaffins. With the development of technology, currently the 4 hydrocarbon groups of normal alkanes, isoparaffins, aromatic hydrocarbons, and cycloalkanes have already become the components of SAF today. Different types of jet fuel have different energy density properties and thermal stability properties, and also they represent different requirements for the sealing capacity of the fuel system. That's why currently, internationally speaking, there are 8 standardized technology pathways proposed by Americans, meaning that the Americans still dominate both the R&D side and the production side of SAF, including ASTM D7566 that contains 7 items and ASTM D1655 that contains 1 item. So for 7566, as you can see, they rely upon syngas, and the feedstock involve coal, natural gas, and a biomass. The second technology pathway relies on fatty acids as feedstock, and hydrogen is added. The third pathway relies on sugar as feedstock, and the fourth pathway relies upon urban waste and turn the urban solid waste into aromatics. The fifth pathway relies upon crops such as sugarcane and sweet beets to turn it into alcohol. It's a very popular technological pathway in the United States. And then additional polymerization is applied. The sixth pathway relies upon animal fats, and the seventh pathway relies upon algal oils to convert all algal oils into the intermediates. And the eighth pathway relies on lipids and biocrude, which represents a blending pathway before adding hydrogen. A very important reaction here is the hydroisomerization reaction. The isomerization reaction means that the oils and the solid waste can be converted into an paraffin that has a very high solidify point, and you need to turn it into a isoparaffin when the freezing point doesn't change. The solidify point can improve much more to around -5 degrees Celsius. So this conversion process is very important, and we convert it into kerosene. We turn it into liquid that has low freezing point. That's characteristic of jet fuel. So for us, we have developed 4 generations of jet fuel technology pathway, and our focus on generation 2, 3, and 4, as the first generation has already been eliminated. So the second generation HEFA to SAF HVO, and third FT to SAF.
So the 3 generation of technologies were and are basically based on the isomerization technology on the M paraffin. So we have worked on this technology for 20 years, and it needs a catalyst, it needs a key carrier, and it also needs the advanced process. And for the 20 years, after 20 years of development, our technology is already proved and is ready for commercialization. For example, in this petroleum-based lube oil project, we have already adopted this technology, and this technology has won the patents and advanced technology awards. So this technology is also used in bright stock. For example, it's already applied to the pilot testing of a scale of over millions of metric tons. And this is a pilot test of using the Fischer-Tropsch process, and it can turn the base oil into this high viscosity lube-based base oil. So in terms of the catalyst, the PGM's role in this whole process, well, it is at the core of the catalyst. So we all know that PGM is able to facilitate the reaction of the chemical conversions and chemical reactions. So it is able to hydrate the base oil, and then it can accelerate the process of a reaction. So we have looked into the mechanism of PGM in the chemical reaction. For example, how it can help with the positioning, how to change the size of the electrons, the property of the electrons. We have also worked on its more detailed mechanism. Based on this research, we have applied for the patents, and it was later developed into processes as well. So based on this technology, we developed 2-way technology pathways. So we would recommend the second one, the one-step pathway. Basically, using the PGM catalyst with one step, the animal fat or the waste can be turned into the SAF using the hydrogen deoxygenation or hydrogen decarbonylation. But of course, there are 2-step pathways as well, as you can see on this diagram. So these 2 technology pathways all use PGM catalyst, and 1 metric ton of the product would need 4 to 5 kilograms of PGM. The PGM can be recycled because it's simply a catalyst. It would not be consumed. So if we can roll out this technology in the SAF market in the future, if the SAF can reach 300 million metric tons in the future, then I think it would use PGM of 200 to 300 metric tons. And also because of this technology, well, the PGM can totally be recycled and reused. This chart shows you the properties of the SAF using the HEFA process. So basically, this technology added hydrogen into the base oil, and it also needs this process we call the hydroisomerization. We take the palm oil, the stearic oil, oleic oil, linoleic acid oil to be the base oil, and we can basically achieve the conversion rate of 100%, and the paraffin selectivity is also 100%. In terms of the hydrocarbon production rate, it's over 80%, and the cracking selectivity and the isomerization rate is over 90%. We have also done a 1,000-hour stability test. With this test, we can predict that with our HEFA technology can be used for 4 years without any changes to its properties. Basically, in this 1,000-hour stability test, we have analyzed the product selectivity, the components of the final products, and from this chart, you can see that the fat is totally transferred to isoparabens. And if you look at the HVO diesel product performance, then you can see that our condensation point is meets the demand of the SAF, and the freezing point also meets the demand. This high quality SAF can also produce a side product, the biodiesel, and the biodiesel. This biodiesel or HVO diesel has a condensed point of minus 30 degrees, and the C10 is 75. So right now, most of the current products, the condensed point is at 0. So we need to still use the HVO technology to achieve the standard of SAF. So compared with the latest technologies globally, we have a one-step process which is unique in our institute, and it also the global practice and our exclusive approach all use PGM as a catalyst. So compared with the global practice, well, our isomerization process can have 89% of the isomerization rate, the conversion rate, and the paraffin selectivity can all achieve 100%. So overall, we can say that we can provide the whole package solution for SAF. In conclusion, first of all, SAF is the jet fuel originated from renewable resources and waste, so it is totally in line with the carbon neutral and carbon peak goal. It is also an important pathway for achieving the carbon zero goal. And by 2050, we estimate that the SAF can reach 350 million metric tons, so it is a big market. The hydroisomerization is the must-go path for producing SAF. So in this process, PGM plays a very important role. And our institute has been working in this field for over 20 years in producing and developing SAF. We have developed 3 generations of technology, which fits all 8 technology pathways stipulated by ASMT. So these technologies can make important contributions to the SAF development and the carbon zero goal of China. Thank you.